Welcome to Day 15, Introduction to Object-Oriented Programming or OOP in Python. In this lesson, we will explore the fundamental concepts of OOP, including classes, objects, and key features such as attributes, methods, and more. Let's dive in. Object-Oriented Programming or OOP is a programming paradigm that organizes code around objects, which represent real-world entities. These objects contain both data and methods that describe their behavior. OOP offers several advantages: modularity, reusability, scalability. Modularity meaning you can divide your code into smaller, manageable parts. Reusability allowing you to reuse classes and methods in different projects. Scalability, which makes it easier to handle complex and growing code bases. A real-world analogy: think of a car as an object. It has attributes such as color and model, and methods such as start and stop, which allow it to perform actions. In OOP, classes are blueprints for creating objects. They define the attributes and methods an object will have. You can think of a class as a template for an object. To create an object, you instantiate it from the class. Let's take a look at a simple example in Python. Here we have a car class, or it does not contain any functionality yet. We can create an object of this class by calling car. On the object, once the object is created, we can interact with it and assign values to its attributes or call its methods. Every object created from a class can hold data. These are called attributes. Attributes are variables that belong to an object and hold its data. In our car example, we have two attributes, brand and color. These attributes are defined inside the class and we assign values to them when creating an object. Methods define the behavior of an object. These are functions defined inside a class that can manipulate or return data from the object's attributes. For example, we might have a drive method that prints out a message saying the car is driving. Let's combine everything into a complete example. Here we define the class car with two attributes, brand and color. The underscore underscore init underscore underscore method allows us to set these attributes when we create an object. We also define a drive method which prints out the car's brand and tells us that it's driving. When we create an object, we can call the drive method to see this behavior in action. Now it's time to practice what we have learned. Here are some exercises to help reinforce the concepts of OOP. Create a simple class called person with attributes name and age. Add a greet method that introduces the person. Build a class student with attributes like name and marks. Add a method called display to show the student's details. Define a class book with a default author attribute. As a challenge, create a rectangle class with methods to calculate the area and perimeter. Give them a try and see how well you can apply these concepts. To wrap up, today we explored the basics of object-oriented programming in Python. Here's a quick recap. Classes are blueprints for creating objects. Objects hold data or attributes and perform actions or methods. We also covered the importance of attributes and methods in defining the behavior and data of objects. OOP helps make your code more modular, reusable, and scalable. Keep practicing these concepts and we will and you will soon be able to build more complex systems with Python. Welcome to this lesson on encapsulation in object-oriented programming or OOP. In this session, we will explore the concept of encapsulation, including public and private members, and how they help in managing the internal state of objects. Encapsulation is one of the fundamental principles of OOP. It involves bundling both data, also known as attributes, and methods, which are functions that operate on the data, into a single unit or class. This means that the internal details of an object are hidden from the outside world. Encapsulation also allows controlled access to these details through public methods, which leads to more secure and manageable code. In a class, we define two types of members, public and private. Public members are accessible from both inside and outside the class, meaning they can be freely modified. On the other hand, private members are intended to be accessed only within the class itself. By making certain members private, we protect the integrity of the data and prevent accidental modifications. Let's look at a code example. Here we have a student class. The name attribute is public, so it can be accessed directly. However, the underscore grade attribute is private. To access and modify the grade, we use public methods like getGrade and setGrade. This allows us to add validation, ensuring that the grade stays within a valid range. Next, let's discuss the init method, which is the constructor in Python. This method is automatically called when a new object is created from the class. It initializes the object's attributes with values provided during creation. In the car class, for example, the init method takes two parameters, brand and model, and assigns them to the object's attributes. Here's the code example for the car class. The init method assigns values to the brand and model attributes, and the display information method prints out these values. Whenever a car object is created, the init method ensures that the object is initialized with the correct information. Now let's move on to a practical exercise. We are going to create a person class. This class will have private attributes like underscore age and underscore address. We will also include public methods for getting and setting these private attributes. This demonstrates how encapsulation helps in controlling the access and modification of the object's data. Here is the code for the Python class. The constructor init initializes the name, age, and address attributes. The getAge method allows access to the private underscore age attribute, while the setAge method ensures that age can only be updated with a valid value. Similarly, you can add methods to handle the address and any other private attributes. To wrap up this lesson, here are a few questions for you to check your understanding of encapsulation. First, what is the purpose of init method in Python? Second, how do you make an attribute private? And finally, why are getter and setter methods important in encapsulation? Take some time to reflect on these points before moving on to the next lesson. That concludes our overview of encapsulation in object-oriented programming. By using private and public members along with methods like underscore underscore init underscore underscore and getter and setter functions, we can better manage code integrity and enhance the security of our classes. Thanks for watching and happy coding. Welcome to day 17 of our object-oriented programming course. Today we will discuss an essential concept, inheritance. Inheritance is the cornerstone of OOP that enables us to reuse code efficiently and organize it logically. This session will cover its definition, implementation, various types, and practical examples. Let's get started. Inheritance is a mechanism where one class called a derived class inherits properties and behaviors from another class called a base class. It allows us to promote code reusability and create a logical class hierarchy. Key terms to remember are base class, the parent class providing attributes and methods. Derived class, the child class inheriting from the base class. For example, imagine a vehicle as the base class and its derived class could be car and bike. This allows shared properties like speed or fuel capacity to be defined once in the base class and reused by the derived classes. Inheritance is implemented using base and derived classes. In Python, the syntax is straightforward. We have base class methods and attributes and inherited and new methods or attributes. Both Python and C++ let you reuse functionality while enabling extensions in derived classes. Let's look at a simple example. Here's a Python class named vehicle which serves as a base class. The base class defines a constructor to initialize the brand attribute and a method drive that all vehicles can use. This is the foundation of our inheritance example. Now let's derive a class from vehicle. Here the car class inherits from vehicle but overrides the drive method to specify behavior for cars. The derived class builds upon the base class and adds its own unique features. Inheritance also allows accessing parent class members. For example, in the example, dog is inherited from animal, and we are using the speak method from animal using the super keyword. Using super, the derived class can invoke methods or constructors from the base class. Similarly, in C++, the base class : syntax is used for explicit calls to base class methods. Method overriding occurs when a derived class redefines a method from its base class. This allows derived classes to provide specific implementations like calculating the area of a rectangle. Overriding is vital for tailoring the behavior of inherited methods to suit specific needs. There are 5 primary types of inheritance. Single inheritance, a single base class and a single derived class. Multi-level inheritance. Inheritance occurs in a chain-like manner. Multiple inheritance. A single derived class inherits from multiple base classes. Hierarchical inheritance. Multiple derived classes inherit from a single base class. Hybrid inheritance. A combination of the both types. These types help structure complex systems effectively. Protected members strike a balance between private and public access. In Python, these are prefixed with an underscore, such as underscore protected attribute. In C++, they use the protected keyword. Here is an example. Protected members ensure controlled access within the class hierarchy while keeping them hidden from external classes. Let's reinforce our understanding with some exercises. Create a person class and derive employee and student classes with unique attributes like salary and grades. Implement a class hierarchy for shapes such as shape, circle, and rectangle, each calculating its area. Create a base class library to manage books and a derived class public library to track issued books. For a challenge, design a vehicle class and derive car and truck, each implementing a custom fuel efficiency method. These exercises will give you hands-on experience with inheritance. By the end of this session, you should be able to explain the concept and benefits of inheritance. Implement various types of inheritance such as single and multi-level inheritance. Use super and constructors effectively in inheritance scenarios. Override base class methods for customized behavior. In our next session, we will discuss polymorphism, focusing on method overloading and overriding. Thank you for participating. Welcome to today's lesson on polymorphism in object-oriented programming, where we will explore method overloading and method overriding. And in this session, we will dive into these key concepts along with some practical Python code examples. Polymorphism is one of the core principles of object-oriented programming. It allows methods in different classes to be called through the same interface, making your code more flexible and reusable. There are two main types of polymorphism. Compile-time polymorphism, also known as method overloading, runtime polymorphism, also known as method overriding. Let's look at each of these concepts in more detail. Method overloading allows us to define multiple methods with the same name but with different parameters. This is useful when we need to perform the same operation in different ways based on the input. For example, you could have a method to add two numbers, another to add three numbers, or even a method to concatenate strings. While Python does not support traditional overloading, it allows us to achieve similar behavior by using default or variable length arguments. Here's an example of how we can implement method overloading in Python. In the calculator class, the add method can take two parameters by default, but we can also pass a third optional parameter using a default value. This way, we can call the method with two or three numbers. Notice that in this case, Python handles the method overloading using the default argument values, allowing us to use the same method with varying numbers of arguments. Method overriding is a technique where a child class provides a specific implementation of a method that was already defined in its parent class. This allows us to modify or customize the behavior in the derived class that was already defined in its parent class. This allows us to modify or customize the behavior in the derived class while maintaining the same method signature. In the example we see here, the animal class has a speak method, but the dog class overrides this method to provide a more specific implementation. This is a classic case of runtime polymorphism. Polymorphism can also be used in functions that accept objects of different types. Here's an example with the animal sound function. This function accepts an object of any class that has a speak method, whether it's a cat, bird, or any other class with a speak method. By calling animal sound, we can pass in different objects, and the correct method is called depending on the object type, demonstrating polymorphism in action. Operator overriding, operator overloading allows us to redefine how operators work for custom objects. For instance, we can overload the plus operator to add two point objects together. In the example, we have defined the underscore underscore add underscore underscore method to handle the addition of 2 point objects. When we use the plus operator, Python calls this method and returns a new point object with the sum of the coordinates. Now it's time for some hands-on practice. Here are a few exercises for you to work on. Write a program that demonstrates method overloading using variable length arguments. Implement a base class shape with an area method and derive classes rectangle and circle. Override the area method in both derived classes to calculate the areas for these shapes. Create a class employee that supports adding the salaries of two employees using operator overloading. These exercises will help you better understand how polymorphism works and how to apply it in your own projects. Polymorphism is a fundamental concept in object-oriented programming that provides flexibility and reusability. We have covered method overloading, method overriding, and operator overloading along with Python examples. Practice these concepts through the exercises and you will be on your way to mastering polymorphism in OOP. Hello everyone and welcome to day 19 of our object-oriented programming course. Today we will be diving into abstraction in OOP in Python. Let's explore what abstraction is, why it's important, and how we can implement it in Python. First, let's define abstraction. Abstraction is the concept of hiding the complex implementation details of a system and exposing only the essential features. For example, when you use a smartphone, you interact with apps and features, but you don't need to understand how the hardware or software works internally. This simplifies the user experience and focuses only on what's necessary. Abstraction is incredibly important in software development. It simplifies complex systems by focusing only on relevant details. It also promotes modularity and reusability, allowing you to update one part of the system without affecting others. Additionally, abstraction enhances security by hiding sensitive implementation details, making your code more secure and maintainable. Now let's talk about abstract classes. An abstract class is a blueprint for other classes. It cannot be instantiated directly. Instead, it contains abstract methods that are declared but not implemented. These methods must be implemented by any subclass that inherits from the abstract class. However, an abstract class can also have concrete methods which are fully implemented. In Python, we use the ABC module to define abstract classes. The ABC class is the base for all abstract classes, and we use the @abstract method decorator to mark methods as abstract. This ensures that any subclass will provide its own implementation of these methods. An abstract method is a method declared in an abstract class but without an implementation. The purpose of abstract methods is to define a contract that any subclass must follow. This ensures that all subclasses provide their own specific behavior for these methods. Let's compare abstract classes with interfaces. In some programming languages, an interface is a strict contract that only allows abstract methods, while Python does not have a formal interface type. Abstract classes can serve the same purpose by defining only abstract methods. The key differences the key difference is that abstract classes can have both abstract and concrete methods, while interfaces typically only define methods to be implemented. So, what are the benefits of abstraction? First, it allows for code reusability. Abstract classes provide a common structure, so subclasses can reuse the logic. Abstraction also improves security as it hides implementation details from the user. Finally, it makes your code easier to maintain and extend, as changes in one part of the system do not affect others. Now, let's put what we have learned into practice. For today's task, we will create an abstract class called vehicle. This class will have abstract methods like start engine and stop engine. We will then create subclasses such as car and bike and implement these methods in the respective subclasses. Here's a mini project idea, a library management system. We will create an abstract class called library item with methods like checkout and return item. Then we will create subclasses for specific items like book, DVD, and journal. This will help you understand how abstraction can be used to create a structured and scalable system. Let's quickly recap what we have learned. Abstraction helps us hide unnecessary details and focus on essential features. Abstract classes define a common interface for subclasses, ensuring consistency. Finally, abstraction promotes modularity, reusability, and security in our code. That's the end of our lesson on abstraction. Does anyone have any question or need further clarification on any points? Feel free to ask. Welcome to day 20 of our Python course. Today we will dive into modules and packages in Python. We will start by understanding what modules are, how to work with standard libraries, how to create custom modules, and we will finish by exploring packages. We will also walk through practical examples to help reinforce these concepts. Let's begin with an introduction to modules. A module is simply a file containing Python code that can define functions, classes, and variables. Using modules helps us organize our code, making it reusable and more maintainable. This allows us to break our code into smaller, manageable pieces, improving readability and reducing complexity. Python comes with many built-in modules that we can use directly in our code. For example, the math module provides a wide range of mathematical functions. To use it, we can simply import it using the import statement. For instance, using import math, we can call the math.sqrt function to compute square roots. Alternatively, if we only need specific functions, we can import them individually, like this. From math, import sqrt, pi. Python's standard library includes a variety of useful modules. The OS module allows us to interact with the operating system. SYS helps us manage system-specific parameters. Datetime handles date and time, and random generates random numbers. Here's an example of how you can use the OS module to get the current working directory. Import OS followed by print os.get cwd. Now that we have seen built-in modules, let's look at how to create custom modules. To create a module, simply save your Python code in a .py file. For example, let's create a file called mymodule.py with a function greet name. Then to use this module in another script, we mymodule.greet the name. When you create a module, sometimes you may want to run certain code only when the module is executed directly, not when it's imported elsewhere. This is where if underscore underscore name underscore underscore equals to underscore underscore main underscore underscore comes into play. Code inside this block runs only when the script is run directly, not when it's imported as a module. Next, let's explore packages. A package is a directory that contains multiple Python modules along with an underscore underscore init underscore underscore .py file, which signifies that the directory should be treated as a package. Packages allow us to group related modules together. For example, imagine a package called myPackage containing module1.py and module2.py. To use a module from a package, we can use the from keyword. For example, to import module1 from myPackage, we write from myPackage import module1. Then we can use the functions or classes from module1 in our code, such as module1.sum function. Let's take a practical example, creating a banking system package. Imagine a directory called banking system containing two modules, account.py and transactions.py. The account.py module defines an account class, while the transactions.py module contains functions to deposit and withdraw money from an account. In account.py, we define an account class with methods to display account details. In transactions.py, we define functions like deposit and withdraw to modify the balance. You can then import and use these modules in a separate script, providing a simple yet powerful way to manage related functionalities. When working with modules and packages, there are a few best practices to keep in mind. First, always choose descriptive names for your modules and packages to make your code easier to understand. Organize related modules into packages to ensure scalability and avoid circular imports where modules depend on each other in a loop. Now it's time for a mini project exercise. Your task is to create a package called math operations with modules for basic operations like addition, subtraction, multiplication, and division. Test your package by importing and using the modules in a separate script. This will give you hands-on experience in structuring and working with packages. Welcome to day 21 of our Python programming journey. In today's lesson, we are going to apply object-oriented programming principles like encapsulation, inheritance, and polymorphism to build a basic bank account system. This project will give you practical experience in coding and problem solving. Let's take a look at a project overview. Our goal is to create a bank system with classes and derived classes. The system will allow users to check their balance, deposit money, withdraw money, and manage different account types such as savings and current accounts. Now let's discuss the core of our system, the account class. We will need attributes such as the account number, a unique identifier for each account, the account holder which stores the account holder names, and the balance which keeps track of the current balance. The class will have methods like deposit which adds money to the balance, withdraw which allows users to take money out, and check balance which display the current balance. We will also create two derived classes from the account class, savings account and current account. For the savings account, we will add a interest rate attribute, and the method add interest will add interest to the balance. For the current account, the additional attribute is an overdraft limit which lets users withdraw more than their balance up to a certain limit. We will also override the withdraw method to allow withdrawals within this overdraft limit. To tie everything together, we develop a bank system that can manage multiple accounts, perform operations like searching for accounts by account number, depositing or withdrawing money, and viewing balances. Add interest to savings accounts and view all accounts in the system. To make it user-friendly, we will create a menu-driven interface. Here are the options. Create an account, either savings or current. Deposit money, withdraw money, view balance, add interest for savings accounts, view all accounts, exit the system. Next, let's look at the code structure. We will break the project into modules. Account.py. This module will contain the account, savings account, and current account classes. Banksystem.py. This is the main program where we manage the accounts and provide the user interface. Here's an example of the output you might see when running the system. It's a simple menu where the user is prompted to choose an action like creating an account, depositing money, or checking the balance. You can imagine how this interface will guide users through the system's operations. For those looking to go the extra mile, here are some additional challenges you can try. Exception handling. Handle invalid inputs or situations like insufficient balance, data persistence. Save account data to a file and load it when the system restarts. Account closure/transfer. Add features to close accounts or transfer funds between them. By the end of this mini project, you will have a functional bank account system that demonstrates key object-oriented programming concepts. This is a great opportunity to put your coding skills into practice while building a useful application.